Okay, welcome back to AP Precal. So now again, we are continuing with log functions, and this is going to be characteristics of log functions today. So we're going back to the same kind of characteristics we've done before: domain, range, concavity, increasing, decreasing, all that kind of stuff. Okay. And we said before how logs are related to exponents, right? So you're going to have those same characteristics. They're just now going to be the inverse. Okay. All right, so basic things about log functions. That is the basic form, a times log base b of x. And that a is the same a we've been dealing with for like ever since algebra 1. In linear, a would be your slope, right? Whatever you did to your function, whether you multiply it by a fraction, a whole number, a negative, whatever it is. Same thing when we did exponentials, it would be whatever you multiplied by. Although in exponentials, it has that extra thing where it's also your first term. Okay, so it's the same thing in logs. It's going to be your first term, and it's also whatever you're multiplying by, which means it can reflect, it can stretch, it can shrink. The dilations and everything. So same same exact variable we've been dealing with forever as far as what it does to functions, right? Okay. The big difference on logs as opposed to exponents is, your domain and range have swapped, right? When you have an exponential, your domain was everything. Like you were going across the total x-axis from negative to positive. And then your range was restricted to whatever your asymptote was, right? And until we started moving exponentials up and down, your asymptote was pretty much 0. Okay, so now the domain and the range have swapped. Okay, so unless I shift my function left or right, okay, so not up and down anymore, but left and right, then my domain is going to be from 0 to infinity, right? Because the basic asymptote is at 0, and it's a vertical asymptote this time. So let me draw it in there just so that you can see it. All right, so the vertical asymptote, the normal, is at x equals 0. Right? If I move my function left or right, if I do a horizontal shift on it, so we're back to horizontal shifts, then my domain is going to change. Okay? But my range is going to be everything, all real numbers, because you are going to span the entire y-axis from bottom to top. Okay, so basic log function where a is bigger than 0 and your base is bigger than 1. Right? Your base cannot be less than 1, so we don't do fractional bases. Okay, or at least on this one we don't. So b is bigger than 1, so your base is bigger than 1, and your a is bigger than 0, so you haven't flipped this thing upside down. This is what a normal log function looks like. Okay? If a is less than 0, that means it's been reflected, right? And your base is bigger than 1, this is what it's going to look like. Okay, it's just been flipped over like normal. Okay, so like exponents, like exponential functions, logs are always increasing or always decreasing, always going up or always going down. So you don't have any extrema. You don't have to worry about maxes or mins or anything like that, not even relative or absolute anything, right? Yes, and please note, unless they're on a closed interval, so if you have dots instead of arrows, then you could say that you have like a local extreme, right? Okay. And because they are either always decreasing or always increasing, they are always going to be totally concave up or totally concave down. Okay. You don't have any points of inflection. These are not like polynomials. You don't have to worry about them swapping which way they're curving. Okay. So again, like exponents, a little bit easier as far as describing them. Okay, so end behavior, we're going to be doing, limit statements for end behavior, just like before. So those of you who keep trying to write it as an end behavior, please stop. We need to write it as a limit. Okay, so if it's going up, right, like this, then your two end behaviors are going to be as x approaches 0, because that's where your asymptote's going to be, right? And then as x approaches positive infinity, right? So it's going to basically increase without bounds. That's just what a log does. Okay. It's not going, your x is never going to decrease without bounds, right, on a logarithm. So no x decrease without bounds because you have a vertical asymptote. You have a boundary that you have to deal with. Okay, so as x increases, y increases without bounds. Here, as x increases, y decreases without bounds. That's fine. But as far as on the left side, because of the asymptote, you're never going to be going to negative infinity for the x. It's never going to be decreasing without bounds. It can't. Okay, so when we write our end behaviors, again, one side is always going to be whatever your asymptote is, and we'll talk about how we find that, right? X is always going to be approaching your asymptote, and on the other side, x is always going to be approaching positive infinity, period. Okay. Okay, so, and yeah, specifically, if you remember our end behavior, our limit statements, x is going to approach 0 from the right. You're not, or your asymptote from the right. You're never going to be able to approach it from the left. Excuse me. Excuse me. So you do need to actually put down that little plus to get full credit for a limit statement for an end behavior, because you'll always be approaching it going towards the right, never from the left. You can't. It's an asymptote. So let's practice some. Okay, so first one, normal log function. I don't even know what the base is, and it actually doesn't matter. On the left side, as x approaches 0 from the right, my function itself is going down to negative infinity, period. On the right side, the limit of the function as x approaches positive infinity is going to equal positive infinity, period, because the graph is going to keep going up forever. There's arrows for a reason. All right, so now we have one that's been reflected. So that does not change the left side. So that is going to be the limit of h of x as x approaches 0 from the right is going to be positive infinity this time because it's been flipped over. It's now going up. Okay, and on the right, the limit of h of x as x approaches positive infinity is going to be negative infinity. So again, basically take a look. These are just swapped. If you flipped it over, that's the only thing that happens, is that your end behavior flips over. Okay, so this is a normal log function and a is not negative. So whatever it looks like, I know at least that it's going up and I have not changed the asymptote, right? And I'll show you because, you know, horizontal changes are in the parentheses, right? We're going to get to that. You are actually going to see something that's got a horizontal shift and therefore an asymptote change. So this is still the limit of g of x as x approaches 0 from the right. And that's going to equal negative infinity because it is going down. And then on the right, the limit of g of x as x approaches infinity is going to be positive infinity. So again, I'm going to show you what it looks like when you actually have a horizontal shift and it changes that asymptote and therefore your domain and your end behavior a little bit because you're not approaching 0 anymore. Okay, so but this is how you're going to have to write end behavior limit statements for logs, period, because of the asymptote. All right, so let's try some bigger and better. Okay, so concave up, concave down, increasing, decreasing. Okay, so again, if you need a reminder what concave up and concave down looks like, this is concave up, this is concave down, even if it is split into half and half. Okay, so this, as weird as it may look, is concave up, and it is decreasing, right? It's getting more and more negative as far as the slope goes, and it will keep going down forever. That is just the way it's going to go. Now, we're not talking about, you know, decreasing rate or increasing rate because, again, it's concave up. We've taken care of that. So the increasing and decreasing is literally is the graph having a positive or negative slope. Right? That's what increasing and decreasing means, is what is the slope, positive or negative. Okay, so the next one, that is concave down, and it is increasing because it has a positive slope And again, it fits the bill as far as concave down. If you wanted to go through the whole phrase, the reason it's concave down is because it's increasing at a decreasing rate. Right? And that was the definition, that decreasing rate of concave down, way back in the last unit. Okay, so I know this is a normal log, but since a is negative, it has been flipped over, which means it looks similar to the first one. And since it looks similar to the first one, we know that it is concave up and it is decreasing. And that -4 causes that to happen. It causes it to be flipped over, right? So it's now decreasing. Okay, so I'm going to skip this for a second and come back to it. I wanted to show you what it looks like when you have a horizontal shift. Take a look at B and C. Right? As soon as you've been given parentheses, right, with your, what we call the actual argument, this is actually the argument of a log, you know, how this is the base, right? This is actually called the argument, and then it would be considered the answer. So when you write a log base, the argument is the part that's like not subscript, right? It's the part that actually has the X or actually has the number that comes after the log, not down here. That's the base, right? So as soon as you have parentheses in your argument, right, you know you now have a horizontal shift. And these work the way they've done, again, since Algebra 1. Horizontal shifts are always backwards, period. Okay? So this function actually got shifted 3 to the right. If you're getting stuck on what the asymptote is or what the domain or what your, you know, limits for your end behavior are going to be, please keep in mind that the argument must always be greater than or equal to 0, right? So you could actually set whatever's in the parentheses greater than or equal to 0 and solve it. And that means X must be greater than or equal to 3 because you'd have to add 3 to both sides. And actually, I need to change that. It's not greater than or equal to, it is strictly greater than. Because your log actually can't equal 0. There's no way to raise anything to a power to get it to equal 0. So it's strictly greater than. So that means that your domain, everything would have to be greater than 0, or greater than 3 in this case, so it's 3 to infinity. If you were to write your end behavior, again, on the left side, so let's see, the limit of g of x, instead of saying 0, you would now say x approaches 3 from the right, right? In this case, it's been flipped over, right? So that means it's going toward positive infinity because it's coming down. This would also affect, what else did I say? Your end behavior as far as your limit, your domain. And if you were asked what the asymptote is, your asymptote is actually x is equal to 3. Right? So specifically when it's in the parentheses that way, when you have a horizontal shift, this is what it does. So let's try the next one, same deal. 2 plus 2x, right, plus 3 has to be greater than 0. Subtract 3 and divide by 2. So x has to be greater than -3/2. Okay, and again, that's a plus, so I know for a fact it's been moved to the left, but it's also got that, you know, extra number in front of the x. So your domain would be from -3/2 to infinity, right? Your asymptote, again, if you were asked, x is equal to -3/2. And then if you were doing your limit statement, the limit h of x as x approaches -3/2 from the right. And it has not been flipped over, which means the fact that it's been moved is kind of irrelevant in this case, but it's still going to look like that. So on the left side, it's going to be going toward negative infinity. So I wanted to show you the difference when there is an actual parentheses and you're actually going to start playing with this as far as end behavior and all that. So as compared to this one, there's no horizontal shift, so your domain is literally from 0 to infinity. And by the way, the range for all of these, we've already stated this. The only acceptable shortcut for this is all real numbers. There's not really any way to write that as an inequality. I mean, if you really wanted to be weird, less than y, like that. If you really wanted to be weird and write it as an inequality with no actual numbers in it, you can. But writing it this way or writing the statement all real numbers usually works better. I need to check with the people of the test to see if they will accept this as the abbreviation for all real numbers. I don't tend to tell people to use that even in my stats class, only because the people that grade your AP tests are human, right? They're not always math teachers. Some of them are English teachers. Some of them are business people. They're hired to do that. And they may not understand what that symbol is. So I try to make it as obvious as possible. I would write it out in words. Okay, so back to the other part where you're actually going to be solving, knowing that these are logs. Okay, and I know I'm going kind of fast, but I'm trying to make the video short so you can pause and do what you need to. Okay, so we already know that these are log functions. That specifically means that the x's are increasing multiplicatively, right? Which means they are being multiplied by the same thing every single time. So it actually should be fairly easy to find out what it is that you're being multiplied because we're looking for a pattern. Okay, so take a look at the first one. Well, that's times 2, and that's definitely times 2. So my pattern must be times 2, which means since x is being multiplied by 2, k is equal to 4. Right, since that's what the pattern has to be. All right, so the next one. Got lucky. That means we have a few pieces in a row. So that's times 3. That's definitely times 3. That's definitely times 3. So since I am multiplying by 3 to go forwards, that must mean I'm dividing by 3 to go backwards. So what times 3 is 6? We know k has to be 2 in this case. And it is literally since x is being multiplied by 3, k is equal to 2. All right, I'm going to do the last one, and then we're going to do the third one because the third one is going to take a little bit more work. This is a lot like when we were writing exponential functions by hand and you had to kind of figure out what the pattern was by, like, did you add or subtract something to the pattern? We're going back to that for the third one. And that one's going to take a little bit more, so I'm going to do the fourth one first. Okay, so believe it or not, this is a multiplicative pattern. It is a pattern of e. If you take a look, this is e to the first, that's e to the negative second. So it has actually been upped by 3. Even though technically you're adding 3 to the exponent, that is still a multiplicative increase because your base is e, right? And you're multiplying by e repeatedly. So if you want to be specific as far as that goes, what you're multiplying by every single time is you're multiplying by e to the third. Because, you know, you add the exponents in the exponent rule. So you're technically multiplying that by e to the third. You're definitely multiplying e to the 7th by e to the third to get e to the 10th. So multiplied by e to the third. So k is equal to e to the 4th. Okay. All right, so the next one, again, it does not look like it's actually multiplying by anything pretty, right? Like this would be going up by 1, and this would be going up by 2. I don't think it's going up by 1, by 2, by 3, by 4, because it is still technically supposed to be multiplied, right? So it's almost like a quadratic, but let me show you how this works. This is like the exponentials we did before, where you had to fiddle with it and see what's been added or subtracted that kind of messes with the pattern. Okay, so I know 19 is never going to be in a pattern. If I subtract 1, that's going to be, so minus 1 would be, that would be 18, or rather, meaning that I added 1. I'm going to subtract 1, but that means the pattern would have added 1. That would be 6, 4, 3. That's still not working, right? The 6 and the 18 is great, but there's a step between them. So subtracting 1's not going to work. If I subtract 2, that's going to be 17. That's definitely not going to work. So let's try subtracting 3. So 16, 4, 2. Oh, yeah, that definitely works. So now we can actually see that the pattern was multiplying by 2. But then we had to add 3. So trying to show how I would actually write it. It would be log base 2, right? Because you are multiplying by 2 every single time. And then you would have had to add 3, right, to get the numbers that you've got. So if I'm multiplying by 2, technically this should have been 8, but then I have to add 3 to the problem to actually get it to work. So k has to equal 11 in that case. And if I need to do a little bit more with that in class tomorrow, that's fine. Just let me know. And for now, we are done. I'll be back with section 12.